Yes.
Perfect. Okay, that's fun. Okay, welcome. I'm delighted to be with you in this Science Week and to talk a little bit about what satellites can do for us in terms of understanding better environmental changes. Um, we we study and have applied a lot of information on environmental applications of satellites since the early 70s. And you can see here on the screens that such things from running from deforestation in places like Central America, in South America, they can all be monitored thanks to the satellites that can collect information on the same point on Earth at the same time. This is one of the advantages that even can help us to understand, for instance, glacial retreat. But many of us might say, well, will all these things about our pendant or our ideas to work with satellites began? Well, it all has a very humble beginning. Back in 1907, there was a German pharmacist that invented this, the pigeon camera. And this camera flew like a drone these days, but with the difference that at that time, the pigeon flew wherever he or she wanted and got some of the first images. He did invent that idea, and the idea was perfect over time, was applied in the First World War, then was perfected over the Second World War, and once the war was over, people began thinking on how we could launch now instead of just a flying pigeon, how could we send something out to the space? And it was the race for the space that sometimes you might have heard people speak about. And that race from space began with the Russians that back more than 60 years ago launched the first artificial satellite called Sputnik. It's like this one. It was the size of a beach ball, about 85 kilograms, and that was sending beeps around the Earth. Now, when that satellite came again back to the atmosphere, it burned in entry. The one on the right here is the first satellite image that we really had. It was around this month, but it was in 1959. And see, this is quite different from the ones that I show you at the beginning. In this one, the only is a snapshot of the Pacific Ocean and a bit of a wave. So not much information that we could get as detectives of the space from this image. But the technology kept perfecting, and over time, we came to have more and more satellites, such that these days you might have heard or read that we have more than 2,000 satellites that are circling Earth. And 446 of those are what we call the Earth observation satellites. In a way, these are the ones that give us the images, like the ones that I showed at the beginning. However, this race for the space and this constant launch has meant that a lot of junk in space is present, and then we have news like these ones that we have to devise now something to collect all the things, the satellites that stop working once the new ones are launched. So you might say to me, well, this is all nice, but can you explain us a little bit about what satellite images are? And in here, I like that you think of satellite images like the pictures you might take with your smartphone camera or your digital camera if you have one. The digital cameras, satellite images are a kind of photographs, but not exactly the same. They are fundamentally different. So this is the picture of my dog that I took, and I could capture here the light that the dog's fur is reflecting, and the light that the dog is reflecting, and the light of the surrounding is what makes up all these variations in light makes up this image. I could play with this image. This image is using one part of the electromagnetic spectrum that we call the visible part. So the things that our eyes can see, and that's the red, the green, and the blue. We could play around and decompose this image into 3 layers, one for the red, one for our dog in green, our dog in blue. And this is the way in which the images are formed. So variations of the different light in the red, green, and blue is what gives us this composite picture. Think on something similar but then at 800 kilometers over in the space. With the difference that instead of a camera, what the satellites work with are with sensors. And those sensors they work with called image spectroradiometer or spectrometers. They collect energy from the sun, energy that hits an object, in the visible light, and another part of the spectrum that our eyes can see as this infrared, the near infrared, the shortwave infrared. So the satellites goes around the Earth once every 5 or every 16 days, same point on Earth is collecting information in the way of emitted or reflected or absorbed light. That light is what is collected and is what makes our images. So in a way, it's like a picture, but not totally the same, because we can play then with those bands. Once the satellite is passing on the Earth, this image spectrometer that you see here on the right is collecting all this information about energy that is reflected from the objects on the Earth to the sensor on the sun. Those images are collected and they are apportioned as bands. Every band covers one part of the electromagnetic spectrum. But when it's collected by the satellite, we get it in levels of grays, kind of seeing the world in shades of grays. So in this band here, this is how I see the shades of gray that correspond to the blue part of the spectrum. While in here is what your eyes, my eyes, cannot see, which is the infrared part of the spectrum. When I combine, like in this example here, I get the blue, the green, and the red bands of this satellite, and I do what we call a natural color composite. But I can also play a trick, and I can use the near infrared or the shortwave infrared, the part that my eyes can see, because I know it has information that is quite useful, particularly when I'm looking at vegetation, because we know that vegetation reflects a lot on the infrared part of the spectrum. And now see that I have chosen these 3 images that you can see here. I take these images here, and I did this, what we call a false color composite. And voila, now instead of green, all my native forest in this area of New South Wales is red. The water is black because all the energy the water absorbs all the energy in the infrared part of the spectrum. So now we said, how do you know that what you see is what you see? Well, in the same way that we sign, everybody has a different signature. Well, objects on Earth do have their own signatures, but unlike us, instead of writing it up, the way their signature is formed is because of variations in the chemical and the physical composition. And the chemical and physical composition of the object is what makes the amount of reflectance in the different part of the spectrum. So you have here in the y-axis how much an object is reflecting, and that how much reflectance is coming from the object is what ends up going to the sensor that is on board of the satellite. And the y and the x-axis is telling me what part of the spectrum. So this is what we call the spectral signature of a soil, which is different from the one of a healthy vegetation, and is certainly different from the one of clear water, and is different from the one of water with phytoplankton or with algae. So it's those clues that we use to try to understand what are all these different colors or this level of grays that we see from the images that the satellite is collecting from us. Now we could say, well, what other clues do you use? And yes, we use the spectral signature is one of our clues. The other clues that we tend to use is trying to have an understanding, if you think being the Sherlock Holmes of the space, and you remember what the teachers tells you in geography and environmental science, they will always say, look for the context, look where the things are happening, look where the landscape is. So sometimes we need to know, because colors might be similar, we need to look at our the landscape that is around us. And we use the clue of the landscape and the clue of the spectral signature. So we know then that if the vegetation is healthy, it will reflect a lot in the near infrared, and it will absorb a lot in the red part of the spectrum. That's one clue that we use. And then we look also to other clues that such as the spatial resolution. What is the smallest object that this satellite image is showing to us? And I have here one example. This is an image from a satellite called Landsat that has the smallest object that it can see is about 30 by 30 meters. The same exactly area as it's seen from an image spectrometer on board of an aeroplane. So now see that in here you can see all the small trees within this paddock, and you can see the water dam, and the same in this aerial photograph. So for us, when we try to understand or to decide which one of these 446 satellites we want to use, one of the things we think is, what do I want to see? Do I want to see something in much detail, or am I happy to have a picture of half of the size of Australia so that I can understand patterns? So this is something important, and then this is something that we can also use to look for clues. Like in this example of the satellite image from a French satellite that is called Spot. And this French satellite in 2016, a colleague of mine was like looking through an inventory and saw this proposal of marriage that was written on this paddock. So I said to you, what do you think might be the pixel size of this satellite so that from 800 kilometers could take a picture of this proposal of marriage? It was about 6 meters. That's the size of this pixel, the size of the smallest object that this Spot image is showing. So that's one of the clues that we use. And the other is time and patterns. And we said patterns are important because they help us to understand stories. And in this example here, I have one story from a place in the Amazonia in Bolivia, so the part of South America, where an image is from the 80s, and all what you see in red here, all these patterns that you see like little bumps, this is forest, is tropical forest, rainforest. And then it's showing to me here these geometric patterns, when we also know that whenever something is man-made tends to be geometric. So there is some form of lines, or there are squares or rectangles. In this case here, is showing to me how this forest is beginning to be cleared up to have fields of soybean. So this was in 86. And then in 2001, the satellite, as it can come always and repeat and take the picture on the same point on Earth every X number of days, 5, 16, I can have images over the years collected. And then I can inquire those images, how things change over time, the dynamics that we say of the landscape. And in 2001, see how much of this area, hardly anything is left of forest. All the forest is gone for these patterns that are soybeans that in the center have a small town, and the towns are connected by roads. And then we have also some forest left on the sides that they use as windbreaks to avoid that the soil erosion, so that the soil is blown up by the wind. So this is the other clue that we try to use to understand the patterns and how those patterns, how the landscape change over time. Now you might ask me, well, how do I use those clues? And well, we use the combinations. Sometimes we know very well that things, something that I see green can be green or can be brown, or I can relate that if it's water with is a lake with sediments, is something that will show brown on the image. Other times it's not that easy because see yourself, if we go out to a park, we see different forest types, different species, and they all look green, shades of green. So If you're a satellite and you have a sensor on board, it's the same issue. Sensors everything looks like kind of different shades of green. And sometimes, even when we know that we try to map different species of forest, things will look quite similar. So the question that you might also say to me, well, how do you know that the satellites are telling me a story that is true and this is not a fake news? Well, we combine the information from the satellites with what we call field verification. And we have in situ sensors many times. So we integrate in that information that we collect from these sensors in the field, like in this example here, these are instruments that we put on the field at this time of the satellite pass so that we can have information about the soil moisture. We can have information about temperature, about wind speed, and all that information help us then, or we use that information with the signal that we get from the satellites and to produce models that can predict yield, that can predict nitrogen contents on plants, that can predict levels of nitrogen in the soil itself, on the topsoil. So now you might say to me, well, yes, you haven't retained us. You told us a lot of theories so far. So what have you done? And this is in the part of my presentation where I like to tell you a little bit about things that we have been doing through one of our projects that where we are looking using satellite images from a satellite that is European called the Copernicus, and the Copernicus has one satellite that collects images on the visible and the infrared part of the spectrum is called Sentinel. And with that one and with partners from Europe, we are developing products that can help, or we hope that they will help farmers to have a better tools for making decisions when sometimes you need to divide your paddock in areas for applying more fertilizers so that you can guide in the application of fertilizers, but that you can also understand how, for instance, an area might be getting too dry that you need to have it more irrigation or not. So this is the website of our project that we began 1 year ago. The products that we are using have been developed and trialed in Europe, and we are now trying to adapt them to areas of New South Wales and Victoria within the Murray-Darling Basin. So within that project, we are using the bands of the visible, the near infrared and the shortwave infrared of this program that is called Copernicus and has the Sentinel satellite on board. And for that, then our teams of experts from University of Melbourne, from the University of Castilla-La Mancha in Spain, and from Austria and Italy, they are trying to develop different products like crop monitoring products, crop yield model products. We are trying to develop management zone maps, nutrition, nitrogen nutrition index maps, and fertilization maps. So all this we are working with farmers in the area because we don't know if the things that we are getting or the things that the satellite and our models are telling are in fact what is happening in the field. And therefore, we have sensors installed and we do ground data collection. Some of our teams are doing ground data collection in the area. And you can see here some towers, some stations that we put in different crop areas to gather information at the same time of the satellite path, again, because we need to understand what the signals means. The signals might mean many different things. Therefore, we have to have that information from the field. This is another example of in situ that we call the sensors that were installed. Here is a weather station, soil moisture sensor in one of the other farmers that is collaborating with us. Also, the team of the University of Melbourne is having some field survey campaigns. So what is growing, where is growing, how is growing? And in here you can see that the same sensor that is on board of the satellite, something similar called a handheld spectroradiometer, is what they use to have a signal as a spectral signature of this crop here, so that we also understand how from close by the spectral signature of this crop looks like. And we also complement that with some airborne, some sensors on board of an aeroplane. So you see that we have a lot of different instruments at different, what we call at different scales, from the field up to the 800 kilometers that is the satellite flight. With those, we produce example of products like this one here, where we have a map that is showing what we predict might be the average potential yield according to some of the conditions of the soil. And then based on these maps of all these little circles and patterns that you see, is what we could use to work with the farmers to advise what areas might be expected that you have less than average expected crop yield, just as previous years, or whether you might have an yield over the average. And that information in the case of this paddock is what we did use to produce what we call the management zone map. So it's expected that then this map can be put in some of the tractors and some of the field equipment that the farmer will be using. And with that, they can apply fertilizers as needed according to the zone management maps that we have derived. And in this example here, which I hope it works, I have to. This is an example here that we had to show how we have this point in the paddock, and our colleague in the farm did have a camera. So he was taking images constant of how the crop was evolving over all the growing season. And each of these red points that you see here are acquisitions of the satellite image that we were processing. And then we use that understanding of how the crops are changing over time to understand the cycle of growth, the cycle, like in this example here, when the canola crop began to flower. And for instance, it was nice to see that one of the algorithms that we apply shows that there is a decrease here on the reflectance that is shown in the satellite. And that is because in this particular part of the spectrum that we are showing, the flowers of the canola are not reflecting much in the infrared, and therefore we have this drop. So we use this. This was an interesting exercise for us to understand how the satellite is changing the signals according to the crop growth stage, or what we call sometimes the phenology of the crop. Okay, so back to our story. We have developed a demo that I was hoping to be able to share with you, but I'm in lockdown in my house with an internet that is not to be trusted. So I put here for the teachers that are present how you can access after this talk. You can access the website, and through the website with this username and this password, take the picture. You can have a look at what we have developed there, and you can run your own, see how you can choose a point in the field and follow that point in the field through time with the different satellite images that we have collected for that site. Okay, so that's what we did with agricultural areas. But then the other part that I put in my talk is what can the satellites do to look after the environment. When we were with Pony thinking about this talk, we were thinking, well, what could be of interest? Well, we thought on Menindee Lakes, that is not far from the areas that I was showing to you before. And some of you might remember that in 2019, we had a lot of news like these ones that were saying, well, there have been a mass killing of fish, and it was an extraordinary event where we have what some people say, a bit of consequences of mismanagement, but also a drought that was unusual. And the combination of these two things, the drought, environmental, the extraordinary droughts, plus a bit of lack of care in terms of managing the water resource, it leads to this massive fish killing. There was an inquiry from the Australian Academy of Science and others in the aftermath, and it was said that that the conditions were there for us to have an extraordinary event with algae bloom. So I'm showing here a series of satellite images that show how dry the area was by December 2020. What you see here is the image totally dry, and now how after 2021 we began having the rains up to what was August of a week ago, where you can see all the lakes that are full of water. The water is blue because I have used a combination of satellite image bands where the blue is for water, but this water is full of sediments. So in this example here, I have used the shortwave infrared and a combination of blue and green, and the water that is full with sediments is showing in a beautiful blue. But if you go there, it won't be this beautiful blue. It's just the way that we can show and how we can highlight some of the features that we are interested. In my case, I was interested to show to you how the change, say, from the change from April early this year, when these two lakes were all dry, and only the two in the top were filled, up to now August, where they were all full. So this is the pre and after of these Menindee lakes in the peak of the dry season. And as you would see if you were in an aeroplane flying the area, this is how you would see it in a natural color composite. All these lakes are very dry, and this is now in the months of May, August, using this trick of shortwave infrared and green bands of the image to show that the lakes are again full. And I did play around with a bit of the images to show to you this red part. This is how you'd see it in a natural color composite. See that you see nothing, you see green and you see a bit of dark gray here. But what I'm interested to show to you here is, see this circle here, this is an area of artificial irrigation. It has lots of crops that are coming up very well. So, and I'm using the infrared part of the spectrum, and this is as a bright red because there is a lot of photosynthetic activity going on here, as well as it is in some of the areas of the lake. So when you have algae on top of the lakes or growing in the lake, these algae will show red because of the photosynthetic activity. So these are some of the clues that we use to know when sometimes you have vegetation on water, like in this example here. So I can use these different, through my understanding of how the spectral signature of algae could be, I can use band combinations to highlight that. And or like in this case, if I would be interested to know how well or how many areas under irrigation are happening in this particular area of Menindee Lakes. So if you want to play with this image, this is another demo that we have. And you can go using this username and password. We have created different layers of color composites and band combinations that let you explore the area back from 2016 up to about a week ago, 11th of August 2021. And you can see some of the images. We have clouds because the satellites we use are called optical satellites. So some of the images will have clouds, and you will not see through the clouds. So you will see the lakes and the cloud of the area at the time of the satellite pass. So, I have 1 minute left. Okay, then I will hurry up a bit. So my 1 minute left is a message. whether you are interested in science, whether you are interested in environmental applications, you are after history, you are after archaeology, always consider that Earth observation can be a key resource to answer some of your questions. You can become a Sherlock Holmes of the space, looking for things, looking for clues. There are ways that you can use, from the very simple ones to the very sophisticated modelings. Earth observation can give input data. We have many universities around Australia that have degrees that include an introduction to remote sensing, but we have also advanced applications. And we are always looking for new work, new questions. We have many doctoral degrees, we have many masters of science that want to do want to inquire, want to do some more applications. And for instance, this is a work of a colleague of mine where that was recently in the conversation. So how we understand the impact of dingoes in a dry lands area of Australia. That was done with the help of satellite image. Then we have this image 3 years ago of scientists using high-resolution satellite images to count penguins in the Antarctic. So you see that the applications are only as narrow as you might be thinking, or you can be very broad in your thinking as well. So with this, I like to conclude this talk, and I hope this has been of an incentive for you to get to know a bit more about satellites. And I thank you for your attention. And to finish off before Bonnie begins asking or getting the image, the questions in the chat, I also have a page of our resources. And thank you, Bonnie, for coordinating all this for me. I like to thank also people of the Koala Project and Turn. So that's the end of my little talk for you, little or not little. Thank you.
Thanks, Graciela. That was great. We have lots of questions already in the chat. So the first question that we have is, is from an anonymous person, and they said, if we have 446 Earth observation satellites, why doesn't Australia have high resolution satellites that can detect fires in real-time infrared as soon as they start, so that they can be extinguished using fast response aircraft before they become out of control? Is there any technical reason why we can't have something like this? It could have reduced many of the horrific fires last year.
Yes, yes, we have. Yes, we have. Australia, we have the technology. There is an initiative from after the inquiry that was conducted on the last fires. All the states have different ways to tackle this, but there is now a really a large initiative that is ongoing between different states, and there is this idea of coordinating efforts of having high-resolution satellites that can help to not to prevent, but to at least have the hotspots in place. Victoria, New South Wales are doing a lot of applied research as I'm talking to you now, and they are combining it with new initiatives and scientists that are trying to also use information from those satellites to try to predict and model what is the fuel load. So there are, I think there are many lessons that were learned after the last fires, and in those lessons there is a lot about better coordination, and it's not lack of technology. I might say that perhaps it's lack of a better coordination, but I think many things are changing. Thanks.
Okay, the next question is from Elsa, and she's 11 years old, and she wants to know if the pigeons who used to do the remote sensing found the cameras comfortable.
Well, I don't know, Elsa. That pigeon is no longer alive, but I think at that time, what that German man that invented, he tried many different types of cameras until he found one that was comfortable enough for the pigeon to still go and do the flight. So I guess the one that flew was one that the pigeon felt that could carry on and take and complete the flights.
Okay, so our next question is from Josh Davies, and he said that the massive fish kills that we see in Menindee lakes are caused by toxic fertilizer runoff and water, which can be caused from monocrop agriculture. And the soil scientists have shown that this kind of farming is destroying soil at an incredible rate worldwide, which is not sustainable. So should we not be fighting against monocrop agriculture rather than assisting it?
Yes, you're right. Sometimes the dominance of one crop can lead to this kind of overuse of certain type of fertilizers that are harming to the environment. So this is why we have advisors, and we have, I think now many of the authorities that are working in the area understood what were the negative consequences of some of these monocrops. I think everything in the right amount can be controlled, but yes, a dominance of one monocrop can lead, as you say, to these negative consequences to the environment, unless there are measures in place, and there can always be better ways to use fertilizers in a wiser way. There are ways to do these days regenerative agriculture or low input agriculture. So it's a bit of that. It's a bit of that knowledge that perhaps needs to happen and to be more mainstream. But you are certainly right in your reflection.
And we have a question from Layla, who's 11 years old, and Layla would like to know what the yellow on the map means.
The yellow on the map. In the big yellow area, there was a big yellow in my map of the Menindee Lakes, and that was all bare ground. That is how, when you have no vegetation in that area, with the colors, with the combinations I did with my satellite bands, this is how bare land did look like.
Fantastic. So we have about 10 minutes left for more questions. So please keep writing in with your questions. In the meantime, I'd like to know what is the smallest object that these types of satellite images can see?
Well, the ones that we call the commercial satellites that you and me can get, Bonnie, we can get objects as small as 1.5 meters these days. Now, many times we say that if we get 1.5 meters, the military satellites might be the size of a golf ball, or that's the smallest object that they might see. But at present, if you go and if you try to buy a satellite image from a commercial company, they will give you some that are up to 1.5 meters.
That's pretty incredible resolution,
Yes.
Given how far those satellites are away.
Yes, exactly. That's how I always think on how far they are on the sky.
Yeah. So where could you actually go and get these satellite images in Australia?
Well, in Australia, we have Geoscience Australia that distribute some of the images I show you up from the Sentinel, the Copernicus Sentinel satellite that belongs to the European Space Agency. They also distribute images from the satellite called Landsat from NASA. And then there are some commercial companies that have these more high resolution satellites that you can buy from them. So you might Google who distributes satellite images, but our entry point usually is the Geoscience Australia.
Okay, and I'd like to know what you think the most critical issue that we're facing is that remote sensing can help us solve.
There are many. The question on the fires, I think remote sensing can be used and it's being used now more and more to try to model what the fuel load could be and to try to have what we call early warning system. So you might read sometimes in the newspaper, we have this early warning system. And that means that we have satellites that can let us know when a hotspot begins. There is one part that I did not cover in my talk, which is the use of the thermal. I was saying to you at the very beginning that sometimes the satellite gets energy that is reflected, and sometimes they have within that sensor that they carry on board, they have a sensor that is specifically done for emitted energy, so the heat. And this is what some satellites use to detect hot spots, things that begin to burn. So with the technology is changing, we have more and more of these satellites that are called constellations, because many of them are launched at the same time, so we can have high repetition cycles. So they can help us with fires, they can help us to monitor things like water pollution that you have seen there. We can also detect illegal deforestation. In the examples I show at the very beginning, satellites are very good to detect these things, and it's not fake news. What you see there is what happens. So for us, satellites are very important in the fight against illegal deforestation, and to get good statistics about how much forest we lose every year around the world, for instance.
It's funny you mentioned the thermal abilities of the satellites. I saw an image a few days ago that was quite shocking to me, that the satellites in space can actually detect magma temperature changes underneath volcanoes and actually show the flanks of volcanoes lighting up as they start heating up, which was something I'd never heard of in all the years I've been working with you now.
Yes, no, they can detect that, and some satellites. I show all the images, which is what I use in my research. But I have colleagues of mine that are interested on emissions from methane, from carbon dioxide, or are interested to understand the cloud movement. So they also use satellite, but they use different parts of the spectrum for that. But you also can, and we can also understand, for instance, ozone layers. When the ozone layers change or get thicker or thinner, all that information comes from satellites. All these maps that you see sometimes with funny colors, these are colors that come from processing not images, signals from the satellite that capture information about the ozone layer.
Fantastic. We have time for one more question, which comes from Elsa again, who's 11 years old. And Elsa wants to know if the map behind you is a satellite image.
Yes, Elsa, this is a whole satellite image from Australia that I got a screenshot from a program called Google Earth. Any one of your friends can go and download Google Earth and have virtual tours of the world, and you can zoom in and zoom out in any place around the world that you like. So it's quite fun to download Google Earth and have it in your laptop.
So I'm going to sneak in time for one final question that's just come through on the chat, because I think it's quite important for a lot of people considering studying these types of things. Somebody said, thank you for a very insightful talk, Graciela. As a university student considering going overseas for postgraduate studies with an environmental management focus, what foreign universities, in your opinion, have a high reputation for specialist expertise in teaching the use and application of satellite imagery? I'm also happy to hear your thoughts on domestic universities too.
There is plenty of them. If you like to research the best one, I suggest you go to the QS World Ranking. of universities, and in there you can check those that are working on environmental science, but you have Stanford University, for instance, in the United States, you have Oxford, Cambridge, you have very good universities in the Free University of Amsterdam. So there are many. Just check the QS ranking, world ranking of universities, and we did within that one put a satellite remote sensing, put geography, or put something around environmental management, and you will get that information. And within Australia, we have many universities again that are that deliver degrees around environmental management and environmental science. At least there is one, like you have in Western Australia, the University of Western Australia, Curtin University, Murdoch University, University of South Australia, Adelaide University, my university, University of New South Wales. You're more than welcome. We have degrees on environmental management, and we do use remote sensing in civil and environmental engineering, as well as in our ecological and environmental management. Then you have the University of Queensland, that they have a large department that teaches remote sensing and uses. Australian National University, a colleague of mine, Dr. Marta Jebra, works a lot with the use of satellites for fire. So I put at the end of my presentation some resources that are also from another network, which is called TERN, Terrestrial Ecosystem Research Network. If you Google that, it will get a lot of area of work that are being open access for anyone that is interested on applications of satellite for environment. You can get from those from that site information about also data sets that you can access for free. So look, there is no shortage of good places where to go and study environmental management and to learn about remote sensing.
Thank you, Graciela. And I've just put the links for TERN and the World University rankings in the Q&A for you, so you can access them. I'd like to thank everyone for bearing with us through our technical difficulties at the start of the talk, and for staying with us through Graciela's wonderful talk about using satellites to detect environmental change. You all have my email address through the Eventbrite ticketing system, so if you do have any further questions or wanted links to resources or anything, please just let us know, and we're happy to get them for you. We'd really like to thank you for your time this week, and I hope you have a great science week and that the other events are fantastic. Thank you.
Thank you.